Hello, so for this video we're going to go over units and just some more standard notations. I want to first talk a bit about, I want to first talk about SI versus US. Just like in any physics course that you may have taken previously, we can use either set of notation. For the most part, we will be utilizing SI or System International as it stands for. Some problems may be using the what we call the British system or US customary system. When abbreviating this, you might hear FPS. That stands for force pound seconds. So if you've ever used SolidWorks or some kind of a modeling software, you might see that there is a option to change what kind of unit system you're referring to. Just to quickly compare the two, and I guess let me just change this here so we can just color code our notes at least. So we'll use blue for that. Okay, let's first talk a bit about SI figures. And we're going to just quickly utilize a formula that we should all be familiar with, and that is Newton's second law of motion here. Force is the product of an object's mass and its net acceleration, and force in that net direction. So if you wanted to quickly just take a look at what units we're referring to for mass, well, the SI unit for mass is kilogram. For acceleration, it's meters per second squared. And so if you wanted to figure out, well, what is the unit for force? It's Newton, right? This is a good refresher for us. But how do we determine what a Newton is? Well, you want to look at the base units. And base units are essentially like the building blocks that encompass this this newer term here. So for us, base units would include essentially these product terms. So kilogram for mass, and then meters per second squared is acceleration. The product of these two will yield a Newton. Let's take a look quickly at an example of the US customary units. And force is measured in pounds, and I know this can sometimes be a bit misleading because sometimes we utilize pounds for mass. So you might see pound force, and that indicates that you're utilizing pounds as a unit of force or weight, for instance. When we step on the scale, here in the US, most or all scales will tell us our weight in pounds. There are other ways to understand weight as well, but specifically it's that. When looking at Newton's formula here, we actually define it not by mass, but by slugs. And it's an interesting term. And essentially what you're looking at is mass is the inertial component of this Newtonian equation here in SI units. A slug is the inertial component for the US unit format. And just real quick, when we look at how to state that, again, you want to look at base units. So a slug is defined, and I kind of have it backwards here. Let me just quickly highlight this. So I have this here, and I have this here. So these two are the same. And if you wanted to look at the base units for force and acceleration, you can look at it this way. So you have pound here, and then you have force there and acceleration here. And so to define a slug, we utilize those base units there. This is something to keep in mind as we move forward. All right. So I'm going to scroll down. These were pre-written notes, and we're going to talk a bit more about primary standards and just how to define certain values that are constants for us. All right. So when dealing with SI units, so let's go ahead and we're yellow for SI. Nobody can read that, so let's make it darker. Mass, kilograms, length, meters, time, seconds. The beauty of time is it's seconds in both, right? That's one constant that we have across the two different conventions. And if you are curious to examine the level of accuracy for a kilogram, we actually have a physical quantity for a kilogram. So you can, for fun, if you're that invested, just look up the International Bureau of Weights and Measures and you'll see exactly what I mean by this. Let's see if my curiosity helps with a quick Google search. International Bureau of Weights and Measures. Sounds pretty fascinating. At the same time, it's also very interesting. But here we go. And, oh, this is, yeah. So with this convention, it's basically related to the measurement science and measurement standards. So there are standard values. They will oftentimes do slight modifications and whatnot, but I'm sure through here you can find certain values. Alrighty, I'm gonna keep scrolling down here so we can keep this video as concise as it can be. And let's talk a bit about gravity. So I want to focus real quick on the left side of this whiteboard. So over here we see G, which is gravitational acceleration. Again, this should be a review of Physics 1, where you may have been dealing with kinematic problems, force problems, work problems, whichever. Oftentimes when the situation or the problem was on Earth, G for Earth is determined as such. We can round this to 9.81 for this class. So 9.81 will be a good approximate there. For if you wanted to use the US customary system, 32.2 is what we can utilize. What's interesting about this is actually depending on where you're located on our planet, it's going to be slightly different. You could actually look up like your GPS and find out exactly what acceleration is in your local area or local gravity. Just for the sake of approximating, we'll use 9.81. But typically the trailing digits may differ a bit. So also, and I guess we'll go ahead and move here to the right side. I'll do that in purple. And over here, what you're looking at is unit conversions. So perhaps you want to convert from one convention to another. There's always a conversion in which we can utilize. For instance, we can always convert from newtons to pound force. And I'm saying equal, and in gray I have it written here, that we're using this as a direct conversion. It's really an approximation, right? And so again, we're just utilizing this to be kind of a fact for us. So for force, we have this conversion here, 9.81 newtons is 2.2 pound force. And then vice versa, you have the, if you want a unit of pound force, how many newtons does that cost you? So for mass, which is right here, 1 kilogram is equivalent to 2.2 pound mass, or 1 pound mass is equivalent to how many kilograms, okay? And then we can also look at slugs. Length, meters and feet are typically the conversions we look at. A very good approximation is 1 yard is equivalent to 3.3 feet. 1 meter is roughly, 1 meter is roughly 3.3 feet. 3 feet's a yard, so you could make a very rough estimate and say that it's roughly the same. There will be some discrepancy, but when doing quick calculations, doing a gut check calculation, which is a calculation that you kind of do in brief, you do a brief calculation with estimates to see if you land within the ballpark. It's good to utilize tricks like that. Now, when looking at the law of gravitation, so this is something that we have to remind ourselves in terms of dealing with statics. In statics, we know that for the most part, or I should say for all part, we're going to be dealing with systems and objects that are stationary. This could be either the fact in which we have no acceleration, no velocity, or we have no acceleration and constant velocity, because the derivative of velocity yields acceleration. So if it's constant or if it's not there, acceleration will be 0. there'll be no change in velocity. But besides that, we may be looking at gravitational attraction. And also, it's just a good reminder of us to consider. Imagine having two masses, which we have right here. I'll go ahead and shade one yellow. I'll make one green. And if you want to determine, well, what is the attractive force between these, that would be this equation here. It's going to consider the product of mass, the universal constant of gravitation, which is given to us. I omitted units though. And also we have to look at what we call the inverse square law, where we are considering the distance between the objects. So we're using r here to depict the distance between objects, and it's squared. All right, why is it squared? That's something we learned in a different class, but I'd be happy to share some neat videos that utilizes or demonstrates how that works. And that's essentially it for this quick review of covering basic topics. Near Earth, weight is mass times gravity. Weight, mass, acceleration due to gravity. All right, that concludes this brief video finalizing the basic topics to review. More videos will come moving forward. We have to do some review with looking at setting up problems, establishing free body diagrams, which are also background topics. So those videos will come moving forward. I think next up in lecture is doing some vector math. So in the meantime, we'll practice our vector notation. All right, thank you for listening and take care. Bye.